Okay, let's just dive right into this explainer and honestly shatter a huge myth right off the bat. The idea that scientific measurements are somehow absolutely perfect. If you've ever stepped foot in a Class 11 physics lab, well, you know that the pristine textbook numbers literally never match the messy reality. So today, we're going to learn exactly how to tame all that chaotic experimental data. Over the next 5 minutes, we're covering our agenda: the reality of measurement, random and systematic errors, rules of error propagation, plotting physics practical graphs, and finally, calculating error in slope. Let's get to it.
Section 1. The reality of measurement. We are officially stepping out of textbook theory and into the hands-on lab, which means confronting the cold, hard reality of imperfect data.
So, ask yourselves, when you're measuring the diameter of a sphere with a vernier caliper or timing a simple pendulum, are you ever actually getting the absolute true value? No way. The fundamental principle of experimental physics is that literally no measurement is perfect. Uncertainties are just baked right into any system. Even the most careful scientist using the absolute best equipment is going to have a slight margin of error. It's just a fact of life.
To really wrap our heads around this, we have to separate two terms that get confused all the time: accuracy and precision. Just picture a dartboard, okay? If all your darts hit the bullseye, congratulations, you're accurate. But if your darts are tightly clustered together way off in the corner, you're precise, but definitely not accurate. And if they're scattered everywhere, well, you're neither. The best scientific observations aim to be both accurate, hitting that true value, and precise, getting that exact same result consistently over and over.
Moving on to Section 2, random and systematic errors. Since every single measurement has this built-in margin of uncertainty, we need to categorize where these errors actually come from so we can, deal with them.
Basically, errors fall into two camps. Random errors are caused by unpredictable fluctuations. Think of your varying reaction time with a stopwatch. The fix for this? Pretty simple. Take multiple readings and find the average. Systematic errors, on the other hand, are constant. Like, if a metallic ruler expands in a hot room, it shifts your measurement in the exact same direction every single time. Averaging won't save you here. You actually have to fix your instrument or recalibrate the whole shebang.
A really fascinating example of a systematic error is called drift, which creates a statistical bias. Imagine a thermometer warming up during an experiment. The zero reading slowly shifts, right? So your measurements are going to literally drift one way over time. If your reading is consistently off before you even start the experiment, you've got a systematic error on your hands, and you have to subtract that from your final readings to find the actual truth.
All right, Section 3, rules of error propagation. So what exactly happens when we take these imperfect measurements and plug them into an equation to calculate a final result?
Well, when adding or subtracting measurements, like combining 3 different lengths to find a total, you can't just add the raw errors together. Actually, notice this square root rule. The absolute random uncertainties are squared, added together, and then square rooted to give you the total uncertainty of the final length. It's like a math puzzle. But wait, what if you're calculating volume by multiplying length, width, and height? Well, when multiplying or dividing, we use a totally different propagation rule. Here, you take the fractional or percentage uncertainties of each measurement, square them, add them up, and then take the square root of that sum to find the final error margin. This ensures the proportional weight of each error is correctly carried through your math. Pretty clever, right?
On to Section 4, plotting physics practical graphs. With all that heavy math out of the way, how do we actually visualize these chaotic errors on paper?
A graph is basically just a picture of a relationship, and plotting it requires some very careful steps to tame the messy errors we just calculated. First up, choose your axes. Second, pick a scale that ideally lets your smallest error division actually be visible. Next, plot those points. And finally, draw a thin, smooth curve or line of best fit. That line? It's your best attempt at finding the true relationship hiding inside your scattered, real-world data.
Now, because of all this uncertainty, a point on your graph isn't just a tiny dot. Say your vernier caliper has a least count of 0.01 centimeters, while your data point is actually d plus or minus 0.01. You draw an error bar to visually illustrate the exact range where the true value could be hiding. It really puts things into perspective.
Section 5, calculating error in slope. Even after you've painstakingly drawn your perfect line of best fit, your final experimental conclusion, which is usually the slope of that line, still has an error margin attached to it.
So, you're going to use this highly specific formula for calculating the error in your slope.
Error equals 4W divided by NR. In your practicals, this simple little formula is a total game changer. It's your key to proving exactly how reliable your final results are, giving you that precise plus or minus range for your calculated slope.
Let's unpack those variables real quick. W is your vertical scatter, so that's the distance between your worst outliers above and below the line. N is just the total number of points you plotted. And R is the horizontal range from your first point to your last on the x-axis. Plug those numbers in, and boom, you have your final error margin.
So, the next time you step into the lab and your readings aren't textbook perfect, honestly, don't sweat it. Acknowledge the uncertainty, apply your propagation rules, and draw out those error bars. The noise isn't ruining your experiment, it's just temporarily hiding the truth. The real question is, are you using the right math to uncover it? Thanks for exploring this explainer with me.